Hello there. In this video we're going to be focusing on a very special type of scenario for which we know some information about the space for which we're calculating probabilities on in order to find the probability of the entire space occurring. Let me draw a picture to sort of illustrate what I mean. So let us assume we have some sample space, or I guess you could call it an event space, S, that is a part of a bigger sample space, and I'm going to represent this as omega. So what if I am interested in finding the probability of this subsample space S? So under some certain conditions, let us assume that the space can be broken up into smaller pieces. Let's assume it as A1, A2, and A3. So if you know information about the probability of A1, A3, and A2 with respect to S, you can find the probability of S with respect to the entire space, omega, and this is known as the law of total probability. Alright, so let's consider the two-set case so that we can easily generalize it to the more general case later. So let's assume our space S is here, and S is broken down into two pieces. I'm going to call it part A and part B. Actually, I'm going to call it A1 and A2. Right? So a couple rules that need to be set here. So firstly, A1 and A2 must both be subsets of S. The second, A1 union A2 must be equal to the entire space S, and A1 intersection A2 must be the empty set. So all three of these conditions must be true. So if this is the case, then we say P, which I define to be the set containing A1 and A2, forms a partition of S. So pretty much it breaks it up into a bunch of pieces, and the sum of all of the pieces is the whole, and none of those pieces share any overlap, right? So that means if you are in this set, you belong to one and only one of these little pieces. Alright, so from the first property, we can get a couple results very easily. Namely, S intersection A1 and S intersection A2. What do you think these are equal to? So you should be able to verify that S intersection A1 is going to be A1 and S intersection A2 is going to be A2, provided that A2 and A1 are both subsets of S. Also, from the picture you should be able to easily verify, or maybe if you're familiar with proofs in set theory, that S intersection A1 intersection S intersection A2 must be equal to the empty set. Now, why is this the case? So S intersection A1 is A1 and S intersection A2 is A2. We know that A1 and A2 are disjoint sets, therefore their intersection is the empty set. So that's pretty much the idea here. Also, S intersection A1 union S intersection A2, what is this going to be equal to? We should be able to verify that this is the set S, using the same exact logic. So that means what? So that means we can rewrite the probability of S as the probability of S intersection A1 plus the probability of S intersection A2. Now why is this the case? So we're pretty much finding the probability of this set, and S intersection A1 and S intersection A2 are disjoint. So we're pretty much using the sum rule that we derived earlier. So I can rewrite this in a more condensed form using summation notation, because the only difference here is that A1 and A2 have different indices. So we can instead rewrite this as the sum from k is equal to 1 to 2 of the probability of S intersection AK, right? We're going to do this because we're going to generalize this in just a moment. Alright, so now I'm going to look at this little piece here. So remember that the probability of S, assuming that AK has already occurred, is going to be equal to the probability of S intersection AK divided by the probability of AK, right? So this is the conditional definition for probability. So I'm going to solve this equation for the numerator of that fraction. So I'm going to get that the probability of S intersection AK is just precisely equal to the probability of AK times the probability of S, assuming that AK has already occurred, right? So therefore, I'm going to extend this definition down. So I have the probability of S is just going to be equal to the sum from k is equal to 1 to 2 of the probability of AK times the probability of S, assuming that AK has already occurred. Right? So I can, of course, extend this down. Generally speaking, we can break this piece S into n little pieces. So we can assume that PS is equal to the sum from k is equal to 1 to n of PAK times PS given AK, where P, which I'm going to define as A1, A2, all the way down to A10, AN, forms a partition of S. So if you do not like this compact form, you can rewrite it in an expanded form if it makes you feel any better. So we can rewrite PS to be equal to PA1 times PS given PA1 plus PA2 times PS given A2 times, or plus, all the way down to PAN times PS given PAN. So this is the law of total probability. Now let us work through an example to sort of illustrate how this is going to work. Alright, so for our example, let us suppose that X is the event from dying as a direct consequence of any one of these diseases, the flu, lung cancer, or heart disease. And let us assume for this particular problem that you cannot have more than one of these diseases simultaneously. We need this for the partition property of the law of total probability, of course, and if this is not the case, it is possible to slightly modify this to the more general case, which we will leave until a later day. Alright, so what type of information do we need in order to solve problems of this particular type? So let us suppose the following cases. The probability of getting the flu is 0.23. The probability of getting lung cancer is 0.35. And the probability of getting heart disease is 42% chance. So Px given A, Px given B, Px given C. What do they mean? So what is the probability of death, assuming that you have the flu? That is, if you have the flu, what is the probability that you die from it, right? So let's assume that these numbers are 2% chance, 51% chance, and 68% chance. Assume. If you want more realistic data, you can definitely research that on your own. So my question is, what is the probability of dying from any one of these diseases? So we know that A, B, and C, if we sum all these numbers up, we get 1, right? So that means the probability of A plus the probability of B plus the probability of C, A union B union C, pretty much total up to everything in X, right? Or the space of diseases, rather. So if that is the case, then what do we know? Now, it is possible that there are other diseases, for example, a brain tumor that can result in death or whatever. But let's assume that these diseases A, B, and C are the only diseases in that space, right? Because it's possible that A, B, and C might not span X, but they span the set of diseases for which we're trying to figure out, right? But in this particular case, we're assuming that all of these span the entire space, so the sum of these should be 1, right? So the probability of X by the law of total probability is going to be equal to the probability of A times the probability of X given A plus the probability of B times the probability of X given B plus the probability of C times the probability of X given C. So substituting each of these numbers, we have 0.23 multiplied by 0.02 and so on. Once you have your numbers down, perform your multiplication next. Once you have everything down, you should find that the probability of dying from any one of these diseases is equal to approximately 0.4687, which is approximately equal to a 47% chance from dying from any one of these diseases. Anyway, that's a particular application of the law of total probability and an explanation of pretty much what it represents. Hope you enjoyed.